we will look at partial redundancy elimination. And we will also look at its development, since it's quite interesting. And then we will focus on a simpler version of SSAPRE. It is published by Kennedy and Shao from Silicon Graphics. And there are two versions of it in the publication. And the simpler one is what we will focus on, and then it can be implemented in a more efficient way. But we will point out what the differences are, but it's much more suitable to start with the simpler implementation. Okay, so partial redundancy elimination. Recall, redundancy elimination is when we avoid recomputing an expression which has the same value. So this is an example of full redundancy. Here it's partial redundancy because this expression might not be redundant if execution goes in this way. But if we go like this, then this a plus b is redundant, and we want to avoid executing it. Okay, partial redundancy elimination can also move code out of loops. So say we have removed this redundancy. That can be done with hash-based value numbering during translation to SSA form. But say we have a loop here. Then the first iteration of this loop, a plus b, is not redundant, but in subsequent iterations it obviously is, assuming a or b are not modified in the loop. Okay, so we have actually partial redundancy here, and we would like to move a plus b to before this loop, and only computed once. What is very neat with PRE is that it can move code out of loops without knowing there is a loop. There is a separate optimization called code motion out of loops, but it's not needed to have, since PRE can do it as well. I mean, we need to have PRE in a compiler, so we use that instead of code motion out of loops. Okay, so it was invented by two French researchers, Morel and Renvoise, in 1979. It uses a bidirectional data flow analysis. Fred Chow, who wrote the optimizing compiler for the Stanford MIPS X project, their research on RISC computers. And in his thesis, there were several different improvements and contributions to optimizing compilers. One of them is a simplification of PRE, and another is or was a different register allocation algorithm. Anyway, a few years later, a German group with Knoop published a version which is optimal in the sense of minimizing register pressure, which the previous versions did not. Okay, and the register pressure occurs when there are numerous registers used for storing temporary variables, such as keeping a copy of an expression that is going to be used later. And it's important to minimize register pressure during optimization. There are several optimizations which can increase the register pressure and then make the program much slower due to a lot of spilling. Okay, so this formulation, lazy code motion, as it is called, produces an optimal placement of the inserted expressions. I mean, we insert expressions in order to remove redundant occurrences of the expression. Okay. Then there was an interest to also have PRE on SSA form. This was regarded as not obvious how to do, because SSA is about variables and PRE is about expressions. And there was even a famous researcher who said that it was essentially not possible to do. At the Silicon Graphics, which together with IBM have the best compiler. I mean, Silicon Graphics does not exist any longer, as far as I know, but their compiler is it was one of the best. Okay. All their scalar optimizations except PRE was on SSA form. So what they did was to do lots of optimizations on SSA form, go back from SSA form to none, and then do PRE, and then translate the program to SSA form again, and continue optimizations. This was obviously not ideal, so they invented an algorithm which can do PRE on SSA form. We will look at a somewhat simpler version which explains all the key ideas and then point out a certain inefficiency, such as we have to redo the SSA renaming of all variables. That is not done in the practical implementation, but we will not look at that, and I refer to the article instead.